Hello, everyone. Welcome to another talk at ACE. I'm Peetak Mitra. I'm a stream owner. I'm a stream owner at the in the machine learning and climate program. I'm a PhD candidate at the University of Massachusetts Amherst, and I'm delighted to welcome Dr. David Hall from NVIDIA for our talk. Before I do that, I will briefly talk about ACE a little bit to all of you. So ACE is a community of machine learning practitioners and researchers who have gathered around topics in AI research, engineering, and products. We host free live sessions like this 3 to 5 times a week and produce premium content in various subject areas. To see more, please visit our website at ai.science and log in to access slides from this as well as other sessions and many more things. Also, please make sure that you subscribe to our YouTube channel, ML Papers Explained, as well as follow us on Twitter under the same name. We currently have about 14 streams that are focused on various machine learning topics, and this session is in the Machine Learning for Climate stream. Hope you enjoyed the talk and come back to us for a talk later on. So we're very delighted to have Dr. David Hall from NVIDIA. And before we let him speak, I'll just give you a brief introduction. Dr. David Hall joined NVIDIA in January 2018 after working as an assistant professor of research in computer science at the University of Colorado Boulder. Dr. Hall has technical expertise in theoretical physics, computational fluid dynamics, numerical methods, weather and climate modeling, and artificial intelligence. Before joining NVIDIA, Dr. Hall spent much of the previous decade developing numerical techniques to improve the atmospheric components of the CESM and E3SM global climate models. As a data scientist at NVIDIA, Dr. Hall's primary role is to translate the latest breakthroughs in artificial intelligence into practical solutions for science and to help train and educate scientists and engineers in the use of these techniques so that they may adapt them to the specific research problems. Dr. Hall earned his PhD in physics from the University of Santa Barbara, California, and a bachelor's in arts in physics from CU Boulder. So we are very happy to have Dr. Hall with us. And Dr. Hall, please take it away.
Okay, thanks. All right, hello, and thank you for inviting me to speak this afternoon. Today, I'd like to present something of a big picture talk on how machine learning can be used to benefit the Earth and to solve some of the world's most challenging problems. So in my job as a data scientist at NVIDIA, I give presentations about machine learning fairly often. And most of the time, I spend time describing what machine learning is and how it can benefit science, particularly the Earth system sciences. But in this presentation, I'd also like to focus on why it might be a good idea to devote your time and skills to these issues. However, answering the question why is necessarily a matter of judgment and opinion, and therefore I'd like to give the disclaimer in advance that any opinions expressed in this talk are my own and do not necessarily represent those of NVIDIA. So, machine learning is new and powerful, and it can be used to do some really amazing things. So with these tools in hand, I regularly ask myself, if given the opportunity to do anything I want to do with machine learning, what should I do? Where does it make the most sense for me to spend my time? The answer to questions like that are very straightforward and very different for different people. But for me, the answer is straightforward. I've always been a big fan of science fiction and a person who thinks a lot about the future. So these days, I have two very small daughters who, unlike me, are young enough to see the year 2100 with their very own eyes. My goal then is to contribute toward making their future the best one possible, which means helping to forge the best possible future for the Earth and its inhabitants. So before getting lost in the details of how machine learning can be used to improve our future, I'd like to give a high-level overview of my thought process. Okay, so first, machine learning provides a new and powerful set of tools which we can use to build amazing things. So what should we do with it? I think one of the best uses of my time is to apply my skills to ensure a positive future for the Earth and its inhabitants. Doing so is not easy, but I'm pretty sure that if we don't, things are not going to end up very well. So if we first clearly identify our goals, then we have some chance to build the tools and techniques needed to achieve them. At a minimum, we should try to avoid catastrophes and existential risks. And in cases where we can't avoid catastrophes, we should at least try to minimize the damage. And I believe all of this can be achieved with the help of artificial intelligence. But we also need to carefully manage the risks imposed by AI itself. In the second half of this talk, I'll delve into some concrete examples of how these goals might be accomplished via machine learning. But for now, let's dive into these points in a bit more detail. So machine learning is new and powerful, but what the heck is machine learning anyway? Since you are an expert in machine learning, or might be an expert in machine learning, I expect you already have a pretty good idea what you think it is, and in fact, you're probably pretty good at it. But everyone tends to think about these things a bit differently, and there are plenty of ways to characterize it. So it's a type of artificial intelligence and a way of finding patterns in data. It can be viewed as a curve fitting exercise or a procedure for fitting a mathematical model to data. It's a means of building a general solution from a specific set of examples, typically in the form of regression or classification. In my opinion, the best way to think about it is maybe a way of building algorithms from experience, which in its current form allows it to act like a new way to build software. Software is composed of a set of functions that take one set of values in and return a different set of values as output. As an example, suppose we wish to build a function to predict how much precipitation is expected within a region, given its average temperature, pressure, and humidity. In the past, there was really only one way to do this. You have to convert expert knowledge into an algorithm, and then manually convert this algorithm into a program running on a computer. These days, there's a second way to solve this problem. We can build a mathematical function that maps the inputs to the outputs and use an optimizer to find the specific function that matches our data. The idea is that once we have properly adjusted the parameters of our function, the function on the right can do just as good of a job of predicting the correct output as can the handwritten version on the left. And for challenging applications, it can often do much better. Machine learning is particularly well suited to operations that deal with complex, real-world phenomena, which are not easily quantified. For example, while you can probably identify the atmospheric river in this image, most of us would find it challenging to program a heuristic algorithm that is able to do so automatically and reliably. In cases such as these, it's simpler to label a large set of examples as containing an atmospheric river, or not, and allow an optimizer to automatically search for the appropriate characteristics that distinguish the two cases. While machine learning and traditional programming can both be used to develop software, they are not the same, and it's important to understand the differences. Traditional programming is labor-intensive. It requires expert knowledge of a subject, but its algorithms are human-readable and usually explainable. Machine learning produces functions by reverse engineering them from data. These functions can be complex and subtle, with an implicit form dictated by the data. They can typically be developed much faster than traditional software, but learned functions can be hard to understand, and they require a different mindset to debug them. Each set of tools has its strengths and weaknesses, and generally the two are most effective when used together in the appropriate way. However, since much of machine learning has only recently become practical, rapid progress is possible by making use of the new techniques. Machine learning is currently being used in much the same way as traditional software, in that the code development and deployment stages are separate and distinct. But this is not how the human brain works. For us, learning and applying what we learn occurs in a tight, continuous, interactive loop. However, machine learning has the potential to grow beyond its current limited role. The primary reason being that both the software and the software developer are made of code. This has the potential to eventually enable continuous iterative training and improvement, which will look a lot more like learning and a lot less like engineering. So machine learning is by no means new, and some of its ideas are as old as computers themselves. When I say that it's new, what I mean is that it's newly practical. GPUs are the tools that make machine learning practical. With a GPU, you can train a machine learning model in minutes or hours. While without it, the same model will take you days or even weeks. And the compute advantage provided by GPUs grows larger every year. While year-over-year performance growth of CPUs has slowed to a trickle, the opposite is true for GPUs. And the latest generation of NVIDIA's A100s are providing 20 times the peak performance of the previous version. Conversely, machine learning makes GPUs more accessible. Not only can you build next-level functionality using machine learning, but these functions are automatically optimized for GPU accelerators. In the end, you have powerful GPU-accelerated software without having to port the code and without having to maintain multiple versions. So with a new and powerful set of tools in hand, the question arises, what should we do with it? Not only is machine learning different from traditional programming, it allows us to build capabilities that go well beyond what we could build before. It's been used to defeat world champions at strategy, to drive cars autonomously, to communicate and translate spoken languages, and to generate original images, videos, music, and text, amongst many other newsworthy accomplishments. While there are many useful things you can build with machine learning, I think a worthwhile goal is to apply it to help address the major challenges facing the planet and its inhabitants. To achieve a positive outcome, we need to develop strategies that consider short-term, medium-term, and long-term goals simultaneously. Most people can relate to this idea when expressed in terms of their personal and financial goals. So, in the short term, you need to earn money for things like food, clothing, and entertainment. In the middle term, you should save for large, important purchases, make decisions that develop your career, and maybe start a family. In the long term, you should stay healthy and save up enough money for college and retirement. If you focus on any one of these to the exclusion of all the others, things will probably not work out as well as you might like. For example, if you focus exclusively on your career, you might never spend any time having fun. Conversely, if you spend all of your money on immediate needs, and you might never save enough to retire. As a group, we also need to address and balance our global goals. In the short term, we need to avoid accidents, avoid getting coronavirus, and vote for good leaders. In the medium term, we need to search for cures for known diseases, prevent wars, evacuate and repair cities when hurricanes hit, and try to improve society by reducing poverty and injustice. In the long term, we should ensure that the planet remains habitable and avoid existential threats and catastrophes, and ensure that we develop and use technology safely. If we want our collective future to turn out well, we need to address all of these problems at the same time. This means looking to the future, anticipating the world's major challenges, and then working backward to figure out how to solve them. An interesting observation is that the short-term goals mostly require individual actions, while success with longer-term goals require us to act collectively or even globally. While all of these collective goals are worthwhile, many of the most interesting and impactful are closely linked with the Earth system sciences. These include preventing climate change to keep the Earth habitable and hospitable for humans, predicting and avoiding weather extremes, mitigating damage when it does occur, protecting the planet from spaceborne threats, facilitating our progress towards renewable energy, ensuring that everyone has enough to eat and drink, tracking the health of our biosphere, coming up with global strategies that allow us to work towards collective solutions, and ensuring that we are using AI safely. Before we work assiduously towards applying machine learning to these problems, first we should address the urgency of these issues. Do these problems really require our active management, or will they work out just fine if left alone? Since ensuring a positive future for humanity and the planet is a goal that would seem reasonable to most people, doesn't it stand to reason that most people will act instinctively for the common good and everything will work out all right in the end? Unfortunately, I don't think so, and there are several reasons for this. One major issue is that, as a rule, people tend to focus on their immediate problems, and they're often too busy to be concerned about long-term issues. Unfortunately, as discussed earlier, success requires us to solve a large set of short, medium, and long-term problems simultaneously. Another reason, as I see it, is that historically, we have found our way by trial and error. And while this has served us passably well in the past, it probably will not work out too well in the distant future. Take climate change as a well-known example. In order to ensure that the planet remains habitable, and preferably comfortable, over the coming decades, all the major economic powers of the world need to make large-scale changes to their economies and the technologies they use. And the sooner they do so, the better. Will this problem take care of itself? So far, the evidence suggests no. And climate change is just one of many significant problems we face. Even if we had a 50-50 chance of navigating each major problem through luck, the odds of us successfully navigating the rocky waters of the future without deliberate planning are infinitesimally small. When you take this into consideration, all the things that we need to get right. So, wait a minute, you might say. The history of the world is chock full of mistakes, and we've muddled through reasonably well without some brilliant overarching global strategy. So what's different about the next 100 years? The difference lies in our technology. The future is not like the past. Our technological capabilities are increasing at an ever-accelerating rate. but our ability to use that tech safely is not currently keeping up. Powerful technologies amplify our ability to influence our world, increasing our interconnectedness, thereby tying together all of our fates. In the past, if two local tribes fought and wiped each other out, or even set fire to the forest they lived in, it would have little or no effect on the people living in some far-flung region or on some other continent. But now, for example, if any two countries chose to have a small nuclear exchange, it would alter the global environment for years to come, producing nuclear winter and widespread starvation. No one can safely use nuclear weapons for war without endangering everyone on the planet. Another obvious example is the current coronavirus pandemic. In the absence of a cure, it's difficult for any country to keep the virus under control in the long term unless all countries manage to bring it under control. Typically, technologies aren't inherently good or bad. Most can be used to both create and destroy. Biotech, for example, can be used to cure diseases, or can be used to manufacture a biological weapon. A swarm of drones can be used to search for disaster victims, or they can be used as autonomous weapons to search and destroy. Heck, even fire can be used to cook your food or to burn down your enemy's hut. Unfortunately, for most technologies, there exists an inherent asymmetry that makes it far easier to destroy than to create. Which is easier, building a tower of blocks or gleefully kicking it to the ground? Even when there's no malice or aggression involved, the use of technology tends to have unintended consequences. Take fossil fuels, for example. People figured out that you can burn them to generate electricity, make plastics, and power your cars. And these inventions have enabled us to increase our overall quality of life, particularly in the short term. But as an unintended side effect, global unchecked use of fossil fuels alters the composition of our atmosphere, harming our quality of life in the long term. Planning for a sustainable future is complex, since each of these decisions interacts with many other decisions, and we need a strategy that carefully balances short-term gains with their long-term consequences. Historically, most of the problems we have encountered have been solved by trial and error. We collectively try things out, and then as something goes wrong, we pass a law or change our behavior to reduce the odds of it happening again. But when dealing with existential threats, trial and error is probably not the way to go, as your first error is likely to be your last. On a related note, Enrico Fermi once famously posed the question, where is everybody? Meaning, why have we yet to encounter other technologically advanced intelligent life? Considering that our galaxy has hundreds of billions of stars, most of which have planets as old or older than the Earth, why are our skies not absolutely teeming with signs of alien life and or technology? In 1961, Frank Drake formalized this question in the form of the Drake equation, which estimates how many civilizations should exist in our galaxy at the present time. While the real numbers for this equation are not known, most estimates seem to suggest there should be quite a few civilizations. The economist Robert Hanson in 1996 suggested that there may be one or more great filters, which severely limit the number of civilizations that make it to the point where we might be able to detect them. One possible candidate for such a filter is the high level of risk imposed by powerful technologies. Any civilization that has the tech to explore the galaxy also possesses the tech to destroy itself, and a single bad day might be all it takes. So, you may have noticed that most of the risks I've described are risks of our own making. So it seems there are three fundamental approaches the world might take in how it handles technology. One, we can continue with business as usual, which is roughly equivalent to close your eyes and hope. Two, we could turn our back on technology altogether, globally limiting its use and returning to some less technological state. Or three, we can continue to develop technology, ever so carefully planning out our path to avoid all the possible dead ends and pitfalls. Option one seems likely to lead to a sticky end, but options 2 and 3 are very hard to achieve, as they seem to require global cooperation and coordination. For example, in option 2, if one country gives up all of its technology, any country that doesn't can just walk all over it. Conversely, for option 3, if any country handles technology irresponsibly, it has the potential to wipe out all the others. It seems like the best option might still be option 3, which is to continue developing technology, but to do so in as careful a manner as possible. This will require us to do many things right and avoid every major existential pitfall. Given the number of things we need to get right, is it even possible to find such a solution? This is a strategy problem, and this is where machine learning comes back into the picture again. We can think of our choices as a high-stakes game, with an action space composed of all the possible individual and collective actions that people can take. If we were to build a good enough simulation of our Earth and its inhabitants, we might be able to find an optimal strategy using reinforcement learning. Is such a model practical? Well, even if it's not, we may still be able to approximate the important parts of the solution in a piecemeal fashion, tackling each problem individually by combining AI and human expertise. So let's think of this as a strategy problem and see if we can plan out the next 100 years safely. The first thing you need to do when trying to solve a strategy problem is to identify your goals. What do you want to happen if things work out well? What do you need to avoid? And how important is each of these? In machine learning terms, we need to identify our goal states and a loss function or reward function that measures how well we're doing. So what kind of future do we want? I think most people would agree that we don't want the kind of future that comes with unchecked global warming, unless you're a really big fan of the Mad Max movies. Keeping the planet habitable seems like a pretty obvious goal. Another possible scenario often seen in science fiction is the kind of world you get as a result of unchecked economic growth. In theory, you might be able to make such a world survivable with enough technology for artificially recycling food, air, and water. But this scenario generally results in the destruction of the natural world, and it looks a lot more like a dystopia to me. The alternative I prefer looks something like this artist's conception, where we aim for a world where we use advanced technology to minimize our impact on the planet, with humans living here but trying to keep the world close to a natural state as much as is practically possible. Some of the sub-goals we should probably shoot for include having a stable climate, maintaining a healthy ecosystem with a diversity of living things, using technology to ensure a high standard of living for all people on the planet, advancing our technology to the point where it almost fades into the background, using AI in a careful and cooperative fashion, and optional future goals might include exploring the reaches of space or terraforming lifeless planets, just so we don't get bored. So, assuming that we can generally agree on the type of future we might like to have, how do we get there? Although we might not have all the details, some major sub-goals seem to be pretty clear. First, we need to make a special effort to avoid catastrophes, particularly the ones that lead to extinction. So, what are the existential threats facing us? Unfortunately, there is quite a large array of showstoppers waiting just over the horizon, some of which are shown here. Step one is making sure none of these disasters come to pass, or, if they do, ensuring that they don't reach existential levels. In some cases, like climate change, it's clear that we are certainly in for some pain, as it's already too late to avoid its effects entirely. In cases like this, it makes sense to try to plan ahead to see if we can mitigate the impacts as much as possible. There are steps that can be taken to reduce the severity of potential threats. For pandemics, for example, we could develop cooperative global strategies for their suppression. On the subject of climate change, we can develop tools to predict extreme weather events, improving the design of our cities and supporting infrastructure and optimizing evacuation and recovery plans. Finally, we should not underestimate the challenges imposed by machine learning and AI itself. As I've said, this tech is very powerful and has the potential to become even more so. In this picture, you can see that computer vision algorithms can automatically detect thousands of faces in a crowd and even identify who's there. This means you are no longer anonymous, even in a crowd of people. While AI can help us solve problems, we also need to take a sober look at the problems it can cause. I'll come back to this and review some of these issues in the last section of this talk. Now that we've identified some of our goals, we can begin building the tools we need to be instrumental to achieving them. Preventing climate change. One of the most important questions we need to address is how to prevent, or at least minimize, climate change. There are many ways machine learning can help here. We can use machine learning to improve the physical models, to speed them up, to make them more accurate, enable higher resolutions, post-process and interpret their output, and more. We can also build purely data-driven models that are able to make specific predictions more directly. We can also use machine learning to help reduce emissions or to do emergency geoengineering of the planet, but those concepts will be broken out into their own sections. The consequences of climate change can amount to anything from a mild inconvenience, to a full-blown threat to our existence, depending upon the magnitude and speed of the change. By making widespread use of fossil fuels, we're changing the composition of the atmosphere, trapping outgoing long-wave radiation and rapidly increasing the mean temperature of the planet. The consequences of changing the climate quickly are many, and they're all bad. So how do we prevent this big mess from taking place? Most simply, we need to replace fossil fuels with renewable energy sources. We can switch to using electric vehicles. We need to build and distribute technologies that can draw CO2 back out of the atmosphere. We should avoid energy waste by recycling. We need to build and improve our climate models so we can predict the consequences of our choices. If all else fails, we might need to resort to geoengineering. Finally, these changes are all tightly coupled to our economic choices. We can prevent climate change by imposing economic penalties that appropriately account for the future costs and damages a given technology is likely to occur. As an example of model acceleration, in their 2020 paper, Mino Veerman and Robert Pincus and their colleagues trained neural networks to emulate the RRT-MGP radiative transfer model. Radiative transfer model equations are particularly expensive and a popular first target for physics emulations. They were able to achieve a speedup of 3 to 7 times the performance of the original model, while retaining a high accuracy of less than 0.12 watts per meter squared in the outgoing long-wave radiation. The plot on the left shows the speed and accuracy they're able to achieve as a function of model size and precision, which is a bit of a trade-off. And the plot on the right shows the vertical distribution of the errors of those same choices. All the models considered were fully connected, multi-layer perceptrons with dense connections, fairly simple models. This type of model emulation can be applied to most or all physical parameterizations, leading to a large potential speedup of climate models. So you can improve climate model predictions also by building more accurate physical parameterizations. In their 2020 paper in Nature Communications, Yanni Yuval and Paul O'Gorman of MIT published a paper demonstrating how to build more accurate parameterizations of the global atmosphere. They used a random forest model to learn a parameterization from coarse-grained output of a 3-dimensional high-resolution idealized atmospheric model. And this parameterization led to a stable simulation at coarse resolution that replicated the climate of the high-resolution simulation. The plot on the right shows snapshots of column-integrated precipitable water for the high-res simulation, low-resolution, and low-res random forest models, respectively. You can see that the default coarse model fails to capture the double ITCZ intertropical convergence zone that's produced by the high-res model. But the physical parameterization generated by the random forest is able to capture it. The plot on the left shows how well each of the low-res models is able to reproduce the high-res mean precipitation and extreme precipitation values. So by producing physical parameterizations directly from data, we're able to construct more accurate versions that improve the quality of our model predictions. In 2020, Prabhat, Karthik Kashinath, and their colleagues at Lawrence Berkeley Lab demonstrated how machine learning can be used to improve the analysis of the data produced by climate models. In this work, they built an online tool that allows climate experts to label extreme weather events like tropical cyclones and atmospheric rivers, which were then used to train a model to automatically detect and segment those storms in future climate simulations. By doing so, they're able not only to produce future storm statistics for many model runs, but they're able to precisely quantify expected changes in precipitation that will be produced for a given region as a result of these storms. By training strong storm segmentation models directly from expert labels, they're able to create more accurate detection routines than it would be possible to code by hand. Chris Cadow, Uwe Ulbrich, and myself published a paper this year in Nature Geoscience that uses NVIDIA's deep learning-based in-painting technique to fill in missing climate data. Historically, observations can be sparse due to the limited number of sensors in place and the limits of seagoing ship tracks, for example. Using transfer learning, we were able to train the in-painting network on data from 2 sources, 20th century reanalysis data and data from the CMIP-5 Climate Model Intercomparison Project. After training, we were able to apply the model to reconstruct missing data from the HADCRUT-4 climate dataset, which in turn enabled us to more accurately reconstruct the global historical temperature record as far back as 1850. We're also able to reconstruct historical trends from modes of variability, like the ENSO El Nino Southern Oscillation. This is an example of how machine learning can improve climate predictions, not just by improving the model, but also by repairing lost or missing historical data. So we might manage to avoid the worst impacts of climate change, or not. But in either case, we can expect increasing incidences of severe weather over time. And machine learning can help us to both detect it and to predict it. As with climate models, machine learning can be used to improve the speed and accuracy of the weather models. It can be used to detect severe weather events from the satellite observations, such as floods, fires, droughts, cyclones, atmospheric rivers, and tornadoes. It can be used to detect forest fires and to predict how they will evolve. And for nowcasting, purely data-driven models can even exceed the speed and accuracy of physics-based models. Physics-based weather models are valuable, though, as they enable us to predict and avoid impending weather disasters like tornadoes, cyclones, and damaging hail. They're also important for forecasting future weather conditions needed to reliably operate renewable solar and wind energy power plants. They help us avoid crop loss by predicting heat waves and floods. And weather models can be used to evacuate cities and to reroute aircraft and boats when severe weather is inbound. Weather models are closely related to climate models, and therefore machine learning can contribute in all the same ways discussed in the previous section. But machine learning can improve weather models in other unique ways as well. For example, they can assist in data assimilation process. Machine learning can be used to thin out and select the most important data to assimilate. It can fill in missing or damaged observations. And we can build functions that transform one type of data into another to allow for data fusion. Also, we can use machine learning to predict a full ensemble of weather predictions from just a few of its members. In their 2019 paper in AAAI, Sheila Alamani and her colleagues from Miami, Florida demonstrated how recursive neural networks can be trained to improve the prediction of hurricane trajectories. They trained their model on data from the Atlantic hurricanes in the Unisys weather database and employed an LSTM-based model taking wind speed, latitude, longitude, track direction, and distance traveled, and grid number as input. The image on the left shows training points in the Unisys database, while the image on the right shows randomly selected hurricane trajectory predictions, which closely match their actual trajectories. This technique is said to have comparable accuracy to the current National Hurricane Center predictions, but it's far faster to evaluate, taking only seconds rather than hours. In March 2020, scientists working at Google Research demonstrated a model called MetNet that produces 8-hour precipitation forecasts that exceed physics-based weather prediction models both in speed and accuracy. The output of their model covers the continental United States at a resolution of 1 kilometer, a time resolution of 2 minutes, and the predictions only take seconds to produce. Model inputs include radar and satellite data, and the output is a probabilistic precipitation map. The figure on the left shows comparisons of the model predictions with both the physically based model and the ground truth observations. The plot on the right shows the F1 accuracy score of the MetNet model when compared to the physical model and the best available optical flow technique. The speed and accuracy of this model shows that purely data-driven solutions have the potential to exceed the performance of physics-based models, at least in some instances, like predicting the weather over a short time frame. In July of 2020, Ryan Lagerquist and his colleagues published a paper in Monthly Weather Review in which they trained a deep convolutional neural network to predict the likelihood of tornado formation within the next hour. The model takes as input a storm-centered radar image and a proximity sounding from the RAP Rapid Refresh Numerical Weather Model. It achieves an AUC receiver-operated characteristic curve value in excess of 0.9, indicating strong prediction accuracy as shown in the figure on the left. The figure on the right shows the best and worst predictions made by the model. With models of this type, we're able to improve the speed and accuracy of tornado predictions, enabling people to seek shelter in time to avoid them. In April 2018, researchers at the University of Waterloo published a paper describing how reinforcement learning could be applied to learn wildfire dynamic models from satellite images. This approach inverts the usual reinforcement learning setup, since the dynamics of the corresponding Markov decision process is a known function. Their results indicate that reinforcement learning was able to outperform supervised learning models much of the time for this project. Models such as this allow us to better predict how a forest fire will grow and develop, so that we can fight it more effectively. On a more general level, this research shows that it's possible to effectively model the dynamics of a system or agent inversely from its behavior. Another important goal for a positive future scenario is to ensure that everyone has enough to eat and drink. While this is already a challenge today, we can expect it to become far more difficult in the coming decades. As the number of people increase and as climate change increasingly disrupts our weather and our growing seasons. For example, a single significant drought or flood can destroy many crops, as can heat waves or invasive plants or animals. Furthermore, it can be difficult to know where and when to plant crops when rainfall patterns keep changing. Machine learning has great potential to help us grow food more efficiently, robustly, and with smaller environmental impacts. Machine learning can avoid crop damage by helping predict where and when droughts and floods and heat waves are likely to occur. It can help us minimize the use of pesticides, producing successful crops at lower cost and with less waste. It can help us track the number, distribution, and health of important pollinating species, like bees. It can also help automatically detect and treat crop diseases. Finally, from a strategic point of view, machine learning can help predict food requirements and potential crop yields to ensure that the supply is adequate to meet the demand. Weeds are responsible for the majority of crop loss, and farmers usually control them by spraying fields uniformly with herbicides. This is expensive and dangerous for people and the environment. What is needed is a precision approach for applying herbicides precisely where they're needed. We can potentially combine drones and machine learning-based computer vision to identify weeds automatically. But weeds look so similar to the crop plants that it's very hard to build a labeled data set. In this 2019 paper, a group of French researchers came up with a very clever way of solving this problem in an unsupervised fashion. First, they detect the crop rows automatically. Then they find the weeds between the rows. These images can then serve as the training set needed to train a convolutional neural network. This approach is as accurate as supervised learning, but with far, far less work. In order to ensure that you're producing enough food, you have to be able to predict crop yields. This can be done fairly easily in developed countries, where detailed farm survey information is available, but it's challenging in developing countries. In 2017, a group from Stanford developed a novel technique for predicting crop yields directly from satellite observations. In their model, satellite images are converted to histograms of multispectral pixel counts. And then the time series of these histograms are predicted with an LSTM network. Finally, the predicted histogram is mapped to the expected crop yield using a convolutional neural network. This technique was tested on US soybean fields and found to perform far better than previous techniques, with a mean average percentage error of only 3.3%. As residents of planet Earth, we're just one component of a large interconnected biosphere, and it's pretty important to maintain the overall health of this biosphere. Machine learning can help with this by helping us to keep tabs on plants and animal species, tracking their locations, numbers, and health. And we can also monitor the state of the environment directly. The oceans absorb the vast majority of the carbon dioxide that's been added to the atmosphere. And without that effect, the change in the average global temperature would be much larger than we are currently experiencing. However, this uptake of CO2 is not without consequences, as it alters the pH level of the ocean water. When the water becomes too acidic, it can kill off the microbiota that are the basis of the ocean food web, thus endangering our own food supply. Therefore, it's important to keep track of ocean acidification on a global scale. In 2019, a paper in the journal Remote Sensing of the Environment demonstrated that it's possible to use machine learning to accurately estimate the acidity level of the ocean from remote sense data directly. This group trained a random forest regression ensemble model, RFRE, on MODIS satellite data and experimentally measured observations of quantities such as surface salinity, chlorophyll concentrations. Their model is able to predict ocean acidity with a 1 kilometer resolution and an R2 coefficient of determination of 0.95. One can only truly determine the health of the biosphere by tracking the numbers, distribution, and health of the plants and animals living within it. This is particularly important for endangered species, as species extinction is generally irreversible. Whales, in particular, are an important species that we would like to keep tabs on, but it's surprisingly hard to get a global picture of their numbers. In a 2019 paper published in Nature Research, a team from Spain demonstrated that they were able to gain an accurate whale count in a very inexpensive manner using images from Google Earth. They trained two distinct convolutional neural networks, one that identifies active whale regions and a second that identifies whales within an active region. They achieved an F1 score of 81% accuracy in detecting the whales and a 94% accuracy in counting them, giving a 34% improvement overall from the previous best approach. Many of the problems we will face require global cooperation to solve. This requires us to first identify what global strategies we need, and then to convince the world to adopt those strategies. Determining global strategies is a task that is well suited to machine learning, and reinforcement learning in particular. Machine learning has demonstrated its ability to master strategic gameplay in a dramatic fashion by achieving superhuman performance in many games. But none was more dramatic than the match between Lee Sedol and DeepMind's AlphaGo in March of 2016. Unlike chess, Go is a game with an enormous branching factor, making it impossible to beat by brute force search, even with the fastest computers available today. In this sense, Go is often considered to be a game of deep intuition. However, DeepMind demonstrated that using deep reinforcement learning and self-play, that AlphaGo was able to learn to play Go better than the world's best champions. In similar fashion, machine learning models have similarly mastered chess, shogi, poker, and many other games as well. Although mastering turn-based strategy games is impressive, most real-world problems are more complex, varied, and continuous in both space and time. DeepMind and OpenAI have demonstrated that machine learning can tackle these sorts of problems as well, by training agents that play as well as the best humans at popular esport games like StarCraft II and Dota. In the StarCraft II challenge, the machine player was intentionally hobbled so that it can perform actions faster than a good human player to demonstrate that it was winning by superior strategy rather than by faster reflexes. They also showed an agent with this skill level could be trained in a matter of just 2 weeks, given enough compute power, while it takes a person years to master these games. What this has demonstrated is that machine learning can be used to easily outperform most humans at strategic challenges. The implications of this to war are obvious, and military leaders around the world have taken notice. This has led to an increased focus on the development of unmanned drones and autonomous weapons. This has the potential to lead to another arms race, resulting in a rise in the availability of powerful smart weapons with an ever-decreasing level of human judgment and control in the loop. When considering military strategy, it's important to keep the global picture in mind as well. Reinforcement learning techniques can also be used to solve a whole host of critical global strategic challenges. Some examples include geoengineering to reduce climate change, controlling the spread of epidemics, preventing global conflicts, and accelerating scientific discovery, amongst others. At the present time in 2020, the COVID coronavirus pandemic is raging out of control in many countries around the world. In the 2020 journal Nature, Public Health Emergency Edition, a team from India investigated various lockdown strategies for controlling the spread of COVID-19. In the absence of a cure, the only way to control the spread of a pandemic is through some sort of lockdown and social isolation. However, lockdowns can result in economic damage that can lead to widespread suffering of a different kind. In their paper, they demonstrated how reinforcement learning can be used to quantitatively optimize lockdown strategies for cities and regions that balance health and economic considerations. Employing ML strategies such as these at a global level has the potential to rapidly bring a pandemic under control with the minimum damage possible and prevent the spread of future pandemics. Another potential strategic target is geoengineering, which is a fascinating but controversial topic. Geoengineering is the process of intentionally modifying the physical properties of the Earth in order to produce the climate we want. Most people consider it to be a method of last resort, to be used only if carbon emission strategies fail and global warming becomes intolerable. One of the most promising approaches is stratospheric aerosol injection, which can be used to increase the reflectivity of the atmosphere, thus cooling the planet. But as stated in the 2019 paper by Christian DeWitt and Thomas Hornigold, using this approach naively can have catastrophic regional consequences, which may induce serious geostrategic conflicts. Instead, they aim to use the power of deep reinforcement learning coupled with emulated physical models in order to predict when, where, and how much aerosol to use in order to maximize the benefits while minimizing the drawbacks. In January of 2020, DeepMind published an article in Nature demonstrating that they could train neural networks to predict the folding behavior of proteins. This is an enormously challenging problem. In the CASP-13 competition, they demonstrated that their approach could predict 24 out of 43 structures, while the next best technique could only get 14 of them. If we can reliably predict how proteins fold, we can greatly accelerate the search for new drugs and treatments for disease. In my last section, I would like to discuss AI risks and rewards. Machine learning is a very powerful technology. Like all technologies, it can be used for many things, both good and bad. The more we develop it, the more powerful potential it has to help us solve our problems. But we need to tread very carefully as it has the potential to create as many problems as it solves. Information technology is in some sense the most powerful form of technology, as it's the one that enables the invention of all the others. But while building new information technologies bring about huge jumps in capabilities, they can have unexpected consequences. For example, DNA and evolution invented our brains, but its goal was survival. Singing, dancing, and everything else we do not directly related to survival is a sort of side effect. Our brains subsequently invented speech, writing, and computers to solve our problems. But who would have guessed all the strange things we would write or the truly odd things we would end up doing with computers? Finally, machine learning is a new type of information tech that has the power to build new systems that we can use, but don't necessarily fully understand. Who knows what the future technologies might be built in this fashion and what unexpected things they might do. While the future is unknown, there are plenty known risks and rewards that seem likely to result from machine learning and AI. These are near-term risks and others are more long-term risks. In the near term, one such risk is the loss of privacy due to facial recognition. Another is that of AI bias, which comes when automating things like loan approval, job hiring, or criminal profiling. Generative models blur the lines of reality, producing deepfake videos and generated text that are nearly indistinguishable from the real thing. And we see automation taking over an ever greater number of jobs that used to be performed by people. In the middle term, AI has the potential to lead to the proliferation of autonomous weapons and the concept of hyperwar, where humans have less direct control. If we look a bit further out, we see risks associated with artificial general intelligence. These include further risks to job replacement, ethical quandaries, the possibility of mind crime. And once we have built an intelligence comparable to our own, one can easily imagine it surpassing us by upgrading its own hardware or software. The main risk from a super intelligent AI is that its goals might be different from our own, as discussed eloquently in the book Human Compatible by Stuart Russell. AGI and superintelligence are highly controversial topics, and experts in the field of AI have a wide range of opinions on when or even if this is possible. But if we were to look into building a strategic plan for the next 100 years, I think they're topics that should be taken seriously and investigated carefully. So, in summary, forging a future we might want to live in will require us to choose our actions carefully, both individually and as a group. A winning strategy will require us to address many challenging technical, social, and economic problems simultaneously. Machine learning is one of the most powerful tools at our disposal, and it can help us to achieve these goals. Many of the most exciting opportunities can be found in the overlap between machine learning and the Earth system sciences. The examples I selected represent a good start, but we have a long way to go. I look forward to seeing what amazing tools and solutions we can build with the help of machine learning. Thanks for your attention, and please feel free to contact me at dhall@nvidia.com.
Thank you, Dr. Hall. That was a very enlightening, very exciting talk. Thank you so much. So we have a few questions from the audience that I will start off and after which I'll ask some questions that I have from my side. So one of the audience members wanted to know, Amir wanted to know, is how did exactly the weed unsupervised thing work? That was, I think, based on that crop problem that you talked about, from somebody from Europe solved it.
So how did the weed thing work?
Yeah.
I mean, it's really not a very complicated solution. It'll take me too long to bring up the slide, I think. Oh, here it is. It's really basically a supervised machine learning detection task, in that you just train it a convolutional neural network to detect, is this a plant or a weed? The problem is getting the labeled data for that. It's really, really hard to get the labels because the plants and the weeds look almost the same. So nobody wants to sit there and carefully segment out all the pixels of a given weed from thousands and thousands of images of crop fields. That's crazy. No one's going to do it. Actually, they did do it a little bit, but it wasn't very successful. So what these guys figured out is they can use machine learning to first just find the rows, which isn't very hard. And then the drones can take images up close of all the weeds that are between the rows. The weeds that are between the rows are the same as the weeds that are within the rows. And so there you have a label, weed, very easily determined.
I
You
see.
can easily remove the weed from the background to get a nice segmented image. So then once you have labels of what weeds are, then everything else is not a weed. And it's a very simple classification problem at that point. Just your standard convolutional neural network classification.
Very interesting. Thank you so much for sharing that.
Mhm.
So the other question was about the tornado evolution problem. I think a professor from Oklahoma talked about it, and Amir again is asking, what is your intuition of why the recurrent neural network is doing better than the physical models?
That's a very good question. I think the main problem with predicting with a physical model, I don't think I really know the right answer to that question. You have to get a lot right. You have to have very high resolution and very high detail to
Sure,
predict a tornado.
sure.
So, yeah, I guess I don't really know, but I think it's just generally simpler to train a machine learning model to do it if you can get enough labeled data. So that was the challenge on the machine learning side.
Sure.
It's a pretty straightforward machine learning thing to find the features that indicate that there's likely to be a tornado.
Sure.
Yeah, I don't really know why it's so hard to do on the weather model side. I'll have to put a little more thought into that one.
Sure. Yeah. So I was very intrigued by your in-painting project, the one you were a co-author on. I was wondering, did you use some sort of like generative network on that? What was the paradigm I mean, what was the workflow, or what was the approach that you guys used?
Yeah. Okay. So we started out with NVIDIA's sort of off-the-shelf in-painting technology.
Was it
And the
Gaussian?
in-painting technology is a masked convolutional neural network.
I see. Okay.
So you input an image and you output an image and you damage the input image and hope you can replace the damaged pixels.
Sure.
And you also input a mask of which pixels are missing.
Hmm.
And the convolutional neural network ignores the masked data and uses just the unmasked data.
Sure.
So that's your standard in-painting technology. Now, the problem is, if you go back far enough in history to where there were very sparse observations, you don't have any completed data sets to use.
Sure.
So you have a couple choices. You can take the few data points you have and damage those some more, but that doesn't give you a lot of points to train on.
Hmm.
So what we did instead, and this was Christopher Cadau's idea, was to use transfer learning. So he took the CMIP model, the 2020 CRAI reconstruction data, and the CMIP model data, two different models. And he used those to train the neural network. So it's basically a simulation. And then once the networks were trained on that, he used that as a basis, transfer learning, essentially, to detect the real climate model data. So we used a little bit of data from the real climate, but a lot of data from simulations, which is a pretty standard approach when you just don't have enough real data.
Sure. Very interesting. So, what does this give you a confidence of, say, predicting, historical trends? Does that give you a confidence that these models would do well for a future forecasting? Like, what are your thoughts on that? Because, a lot of these models tend to fail on that aspect. Like a lot of the climate models, you can predict, historically the trends very well, but some of the future trends, they don't seem to get it right because of the very complicated physics and the nonlinear interactions between these sub processes. So do you think machine learning has any potential in that aspect for forecasting?
Yeah. So the answer to that question is very long and involved, but the short answer is yes. Machine learning has a lot of potential both to predict directly and also to enhance the physical models and allow
Sure.
them to predict.
Sure.
In the case where you're trying to predict, say, a physical parameterization,
Mhm.
and you train it on historical data, you might be a little bit nervous about whether or not it can predict, once you're in a climate change scenario.
Mhm.
So that's challenging. If you go too far away from the data that you've trained on, your
Yeah.
machine learning model falls apart. So in order to overcome that, you have to basically explore the region around your physics model. So not just simulating what's happened, but lots of things that could happen. So if you want to emulate that model, you simulate the real world, but you tweak the parameters, you tweak the temperature, you tweak the forcing, and you explore the parameter space in as much as you can afford to.
Interesting.
And that allows you to expand to lots of scenarios in this parameter space that you haven't actually seen, and it can do a pretty good job.
Sure.
The second thing you need is a classifier that tells you, have I gotten too far away from the stuff I know? Because the deep learning model will give you an answer, even if that answer is wrong.
Yeah.
And we need to know either how uncertain the answer is, or to know if we strayed outside of our training regime and we need to do more training.
Sure.
So there's a lot to that, and there's a lot of work to be done in that area, but I know a bunch of people who are working on that.
That's very fascinating. So one last question, we hear a lot of these giant tech companies, and NVIDIA obviously is one of the leaders in tech. So for example, Microsoft has this commitment to go carbon neutral by 2030. Delta has that too, and machine learning and GPUs accelerators especially have a big carbon footprint. So like, how would you like to see personally? And I hope I'm not putting you on a spot. How you would like to see NVIDIA kind of like take a leadership, because NVIDIA is a thought leader in so many areas.
Yeah, so let's think about this. If we want to simulate the future, we really need to simulate the future, because otherwise we don't. So usually that's done on a giant supercomputer using all of the cores to do a physical model. Very expensive. It uses just draws up as much power as you would use to power a city for a short period of time.
Sure.
When you use machine learning, if you can accelerate that same model, you're getting the same result, doing it faster, using less power.
Sure.
Furthermore, GPUs are more power efficient for an equivalent number of computations by far than a CPU is, because it doesn't do a lot of predictive, predictions. It doesn't do a lot of predictions of where the code's going to branch. CPUs do things in parallel, and they use a lot less power to do the same thing. So on a cost comparison, on a compute to compute cost comparison, GPUs are already lower by, I don't know, at least an order of magnitude, maybe more.
Interesting.
Everybody is driving as much as they can to low power results, because power is money.
Yes.
So, not to be like a giant NVIDIA salesman, but if you look at the recent presentations by our CEO, Jensen Huang, he shows that you can replace like a whole giant rack of like millions of these machines with one tiny little rack of these DGX systems that does the same compute and requires like a very tiny fraction of the power. So GPUs are actually doing a really good job of heading in the right direction, and we need to do more power efficient, power careful computation. So if everybody out there who's listening moves their computations onto a GPU, we'll save a huge amount of power. Now this isn't easy to do, right? Because traditionally you had to learn CUDA and you had to learn how to program a special language. But AI, which is the thing I'm talking about here, is the trick. All you need to do is train data, run it on a GPU, and suddenly you have a piece of software that runs on a GPU at low power, fast, efficient, and better than old software, right? So it's like magic.
That's very interesting. Thank you once again, Dr. Hall. This was fascinating to hear about your experience with NVIDIA, and as well as your personal passion in this area of using machine learning to address some of our biggest challenges that we are facing currently. Thank you everyone for joining in. Please feel free to follow ASEC on our website, as well as come back for some other talks that are coming up in the next weeks. Good night, everybody. Thank you.
Thank you for inviting me.